Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to this session of CHE 409 PC2 data analysis. PC2 is actually about time constant of thermocouples. So it means we put some thermocouples at different environment. Which one of it is the vacuum, and the second one is the bath, which is the hot bath containing water. And also we try to put a shield, which is like a cover, and another time we do it with bare thermocouples. So basically we have the experiment trying to record the temperature, change in temperature of these thermocouples with time. So it means if you take it from, let's say, a vacuum and you put it in bath, water bath, definitely the temperature is going to transit from the room temperature or from the vacuum temperature to the temperature of the water. So it means we are going to record all those temperatures step changes. So usually we have the step change interval to be maybe 1 second, sometimes 5 seconds, sometimes 10 seconds, sometimes 15 seconds. And for that we have a total of experiment from A, B, C up to F. And that data we obtain for time versus temperature are the ones we are going to use for the data analysis, meaning basically to be able to obtain the time constant of those thermocouples. It is very important because if you have a system that you want to use a thermocouple as a sensor and you want a very fast response, so it means you want a thermocouple that has short time constant. And if you want a slow response, then it means you want a thermocouple that has very longer you want a thermocouple that has longer time constant. So it means it's very important to study the time constant of thermocouples. So for the first step we have, which is A, you have the data sheet as like this. You can see this is the data point, the log date, log time, and then the temperature. So the first column, the second column, they don't have we don't have anything to do with them. The main thing that concerns us is this log time and also the temperature. So the first thing you have to do is this time, the first one you assume as what? 0. Then the second point you assume it to be you subtract the first from the first one, then you'll be able to get the difference is 1 second, 1 second, 1 second, 1 second. So you have 0 second, 1, 2, 3, 4, 5 as your time. And then you can see the temperature changes from 23, 71, like that until it reaches 80. So it means 80 is actually the temperature of the water bath. And then 23 is actually the temperature of the vacuum. So now the thermocouple has transit from the temperature of the thermocouple has transit from vacuum temperature to temperature of the water bath. So we have this one as our data, and you can see for the second step, which is B, we have this data. It spans continuous like this. You can see we have B1, B2, B3, and then for the next up to B4, and then for the next one we have C, which is this the third section of the experiment. We have C1, and then we have the fourth one, which is D, D1 and D2, as you can see. And then the next one we have E, which is only a single data because it is from room temperature, from the vacuum 28 to this 76. This one, it is very fast because we have forced convection, that is we use fan to cool the thermocouple. So that is why you see that the transition from the vacuum temperature to room temperature, from the vacuum temperature to water bath temperature around 78 happens within very short time. Still, what you need to do is you are just concerned about the log time and the temperature. This will be your 0, the first one, and then the difference, as you can see, is 10 seconds. So you have to say 0, 10, 20, 30, 40, like that. So this is the raw data we have. The next thing is to go to the data analysis, which is the main business of the day. So as you can see, yeah, we have F here. So as you can see, we have time versus temperature. What we need to do is, if you look at, for instance, this one, you can see that we have values repeating themselves. Or for instance, let's go to this. Yeah, we have values repeating themselves. For instance, if you consider 75, you can see 75, 75. If you consider 76, 76, 76, 76, 77, 77, 77. So it means we don't have to take all these points. We just need unique points. For instance, here that we have repetitions of the temperature remaining constant, so we just pick one of the values such that our graph we are going to obtain is going to be linear. If not, we are going to have a zigzag graph. So just as mentioned here, pick only one value of temperature when it repeats itself, that is when the temperature remains constant. After that, then you try to evaluate the maximum temperature deviation, which is the difference between the temperature at the infinite time minus the temperature at 0 time. The infinite time is actually the last time when you have steady state, and the 0 time is actually the beginning. So the 0 time for this will be 76. The temperature at 0 time will be 78, and then the temperature at infinite time for this case is going to be 28. So the difference between these two values is going to give you A. So you try to evaluate A for all the changes, for A, B, C, D up to F. And then the next thing you do is, if you consider the first change, which is A, or if you consider the second change, which is the B, or this third one, which is C, E, like that, you have to evaluate the temperature deviation, which is just the temperature at any time minus temperature at 0. For instance, if I want to evaluate the deviation for this one, at the first it will be 0 because it will be 78 minus itself. The next one it will be 77 minus 78. The next one will be 74 minus 78. The next one will be 69 minus 78, and continuously we obtain the successive the respective temperature deviation, which is temperature with this temperature would be temperature deviation is going to be temperature at any time minus temperature at 0. It means we can be able to generate a table of this kind. We have time from the raw data, we have the temperature from the raw data, we have the temperature deviation from the processing we did, and then the next we can get the ln of 1 minus temperature deviation over the maximum temperature. So now what you just need to do is, the next you plot ln of 1 minus temperature deviation over A versus time for each step, that is the step A to F. If you make the plot, we expect that the intercept should be 0 or nearly 0, and also the slope will be minus 1 over tau. So it means for each of the step changes you are going to have tau, and then you can discuss which one has bigger or smaller tau and the reason behind that. Now we have obtained tau, which is the time constant for all the step changes, and this is the main thing we are expected to do, and then follow with some inference and deductions, discussions, and what have you. Thank you very much. We're supposed to do the same plot for theoretical deviation in temperature versus time, but the issue is we don't have tau, or we don't have a way to obtain tau using theoretical method, even though we have a formula of tau as mCp over HA. The m is the mass, Cp is the heat capacity, H is actually the heat transfer coefficient, and A is the area. But then we don't know these values for our time constant, for our thermocouple. Thank you very much.